We're going to be writing and balancing. Okay, so we are now starting class, so please stop talking. Thank you. Writing and balancing ionic compounds. In addition to classifying what an ionic compound, ionic and covalent compounds. And then we are going to very briefly start naming ionic compounds, which if you've been in this class before, you know that that is not the easiest subject. We will be, next class, there will be a lot to learn. This class too, but like next class, there's just a lot of rules that you have to know. So yes, so definitely if you're like, if you leave next class or this class and you're like, what the hell did she say? Go to CLC. Naming ionic compounds. And apparently I can't write ionic, so it's legible. I do want to clarify how to count electrons across the periodic table. There was a little bit of confusion in class yesterday. So I'm gonna, if you have your periodic table, have it out. So in class on Thursday, I mentioned that for n equals 2, row 2 and 3, you can use 1A through 8A to determine how many valence electrons you have. Because if you're counting across the periodic table, as you add, so we're talking about neutral elements, which is when you have the same number of protons, the same number of electrons, okay? So neutral lithium has so you're adding a proton here, but you're also adding 1 electron. It's 1 valence electron. And then neutral beryllium has 2 valence electrons, and then neutral boron has 3, and so on all the way to 8. However, when you get down to row 4 and below, you have the transition metals, so you also have to count across there. So when you're saying how many valence electrons, for example, is in vanadium, which is element number 23, you're counting 1, 2, 3, 4, 5. And all the way over to bromine, bromine is going to have 17. Okay, so for n equals 2, so n equals 1, row 1, you can only have 1, 2, right? Hydrogen has 1 valence electron, helium has 2 valence electrons. N equals 2, you can use 1A through 8A, same with n equals 3. And then row 4 and below, n equals 4 and below, you have to use the 1 through 18 system for determining how many valence electrons, or just count across. If you're not sure and you're like, how many does germanium have? You just count from potassium all the way to germanium, and you'll find that you have 14 valence electrons. Okay, so definitely count across. Thank you. Any questions on that? Just wanted to clarify that because there was a little bit of confusion. So yeah, that's when it comes to the neutral element, right? A neutral element is where it has the same number of protons, same number of electrons. However, today we're going to be talking about the ions, which is when those neutral elements are not quite satisfied with the amount of valence electrons they have. Some of them want to lose some of them want to gain some, which is what we learned on Thursday. And we're going to be learning how to take those ions and put them into compounds. First, we have a couple definitions. An ionic compound, so ionic compound has an ionic bond. And an ionic bond is the attraction of between two or more charges. So for example, Na plus and Cl minus. So the attraction between two, tried to combine two or more charges. So this means they don't share electrons. This means that one has lost electrons and one has gained electrons, and because they've already lost and gained electrons, they're going to be attracted to each other because opposite charges attract and stick together, okay? That is an ionic bond, which means that an ionic compound will have a cation plus an anion. That is the general formula of an ionic compound. Does anybody know what a cation, what type of element a cation usually is? It's a metal, usually a metal. Because if you look at the periodic table and all of the elements you circled as metals or you outlined as metals, most of those will form positive charges. Because remember, a cation is a positive charge, a positive charged particle. And the anion, so it's usually metal. I'm going to put usually, because I will come up with an exception later on, as always. And that means your anion is usually a nonmetal. But what's important that you know is that you have a positive and a negative charge. A covalent compound, which we are not going to talk about as extensively today, but you do need to know, is, so a covalent bond is where two elements share electrons within the bond. And these are, and a covalent compound has to be all non-metals or metalloids. So these are things like H2O, CO2, C3H6O3, things like that, that have only non-metals, SiF4, silicon with 4 fluorines. That's all non-metals and metalloids, okay?
For the ionic compound, is that why sodium chloride, sodium and chloride bond together?
Yes, and that is actually, and I will actually, that is always my basic, my first example, because it's the most common example that people have heard of. And I'll talk about why those two pair. I'm just going to give everyone a minute to write this down. Are we ready? Okay. How to write ionic compounds. First rule, cation is always written first. This is why we have, if you have Na and Cl, it's NaCl, not ClNa, right? That just looks weird, It's wrong. So it's NaCl because your cation is your positive ion, and your and that's your sodium plus, and then your anion is Cl minus. And then the second rule is that the overall charge is neutral. In other words, charges must balance. So if you have, once again, I'm going to use Na and Cl. Na plus, the overall charge of that is +1. You'll see why I'm talking about overall charge in a couple seconds, but with Na plus, it's obvious that there's one Na and it's 1 plus. Cl minus is -1. So the +1 and the plus minus cancel each other. The plus 1 and the -1 cancel each other out to make a neutral compound, NaCl, which has a 0 charge. Simple enough. However, it's not always a 1-to-1 ratio. And can I move on to the next slide? No, okay, I'll give you. Yeah, take it away. All right. It's not always the case that your cation and your anion will automatically cancel. For example, if you have Na plus NO2 minus, you start out with an overall 2 minus charge and an overall 1 plus charge. That's a problem. So what can you do to balance them out? Multiply the 1 plus charge by 2. So what you're going to do is you're going to put in 2 sodiums. So you're going to do times 2 because you need 2 sodium pluses to balance out the O2 minus, and that gives you Na2O. So the subscript applies only to the element it is directly attached to. And here we have, so we know that we have 2 times 1 plus, that makes an overall 2 plus charge, balances out the overall 2 minus charge, and we have a neutral compound. We can go in the opposite direction where we have Ng2 plus and Cl minus. In this case, we have a 2 plus charge and a 1 minus charge, so we have to multiply, we have to put in 2 chlorines in order to cancel out the 1 magnesium. So we're going to multiply that by 2, which gives us MgCl2, which is neutral. So once again, that 2 only corresponds to that chlorine, and that's called a subscript. You will also have cases where you can't just multiply one by, like one element by a number, you have to multiply them both. For example, Al3 plus and O2 minus. In this case, we have a 3 plus and a 2 minus charge. And yeah, so we need to find the lowest common denominator, which for 3 and 2 is 6. So we're going to multiply this guy by 2 for an overall positive 6 charge, and this by 3 for an overall negative 6 charge. So 3 oxygens, 3 O2 minuses gives you negative 6, and 2 Al3 pluses gives you positive 6. So our from that, we have 2 Als, because we multiplied that by 2, and 3 O atoms, which means we have Al2O3, and that is a neutral compound. So notice that the subscript is not the charge, it is the number of that type of atom that is needed to cancel out the opposite charge. Questions thus far?
Is there a reason why there's a subscript and not just coefficient next to the AL?
Yes, excellent question. So Mike asked if you have it's the third one? For the third one. So why I put that down as a subscript instead of in front of the AL. Putting a coefficient in front of a compound multiplies the whole compound. So if I put a 2 in front of AlO3, that would give me 2 ALs and 6 oxygens. So you only want it to correspond to that element, which means that's a subscript. So coefficient applies to the whole compound. Subscript only applies to things directly before it. Excellent question. I want to stress that these should be written as the lowest ratio. So I don't want this, for example, to be AL609. It should be AL203. All right. Let's do some practice. I want you to give the compound that forms from the most likely ions of the element pairs I gave you. So you have to determine what the likely ion is from what we learned on Thursday, and then give the compound that forms from those ions. So identify what the charge on each of these elements will be once they gain and lose their electrons, and then pair them up, make a charge balance ionic compound. Katie and Jose are here to help me. Raise your hand if you have any questions. So I wanted that.
Do you want to get him in the room? Is that your question?
Alrighty. Most of you that I saw did a pretty good job, especially on the first one, because I want you to really think what the cation and the anion is. So it actually gave you N first because that forms the anion, and you had to switch the order. What's the most common? What's the most likely ion of N of nitrogen? 3-. And what about calcium? So what do we have to do to both of those? Yeah, we have to find the lowest common denominator, so we have to multiply N times 2 because we want a total of -6 charge, so times 2. And calcium, we want a total of +6 charge, so we're going to do times 3. Which comes first? Calcium, because it's always cation, then anion. So it's going to be Ca3N2. And I want to be very clear that this is how you write an ionic compound. Your final written out ionic compound should not include the charges, okay? Should not include the charges because the charges have canceled out. So don't like write Ca2 + 3, just take Ca3, right? Don't leave the charges in the final compound. What's the charge on potassium? +1. And I accept either plus or +1, either way works for me. And then what about sulfur? It forms a 2- charge, so what do we have to do? Potassium times 2, so you're going to have K2S. And finally, what's the charge on strontium? Oxygen. What do we have to do there? Nada, so we just have SRO. Okay. Yeah. Of course.
How do you know which one was first again?
Okay, so cation is always first. Do you remember what the cation is? It's usually metal, but it's the positive ion. Okay, so positive, then negative.
Okay.
Yeah. So that's why we switched the nitrogen to calcium, because I gave the calcium second, but that's the positive ion. Switch it. Yeah, positive, then negative. Cation, then anion. Let's talk about transition metals. Those are fun. So transition metals can have multiple charges. Which means they can form multiple compounds with the same single charge ion. And now, what do I mean by that? Does anybody know the 2 most common charges of iron? 2+ and 3+. So if I have Fe2 plus and Fe3 plus. So in this case, in the 2 plus, it lost 2 electrons because you lose electrons, you become more positive. Iron 3 plus lost 3 electrons. So if I want to combine both of these with oxygen, the first one is going to be relatively simple because they're already balanced, right? You have a -2 charge and a -2, you have a +2 charge and a -2 charge. So those balance each other out, which means you're going to have FeO. That is going to be your, what we call our iron oxide, which you will learn how to name later. But FeO is the iron 2 oxygen compound. What do we have to do with the iron 3? 2 and 3, we have to find our lowest common denominator, which is 6. So we're going to multiply iron times 2 and oxygen times 3. So we have a total charge of +6 and, oh, sorry, that's wrong. Burp, times 3 and -6. So now we have a Fe2O3, which is once again neutral. So these are both neutral compounds depending on the charge of the iron, which means if you look at this, if you had to identify the charge of iron from two different oxygen compounds, you could say, well, the first one you have iron balances out, one iron balances out the O2 minus, which means that charge on the first one has to be 2 plus. In the second compound, I have 3 O2 minuses, so that means I have a -6 charge, and then the irons have to form a +6 charge, which means that each of those irons is 3 plus. So you can actually identify the charge of that iron based on the compound it formed. These are two different these are two different compounds. They have very different characteristics. This is called wustite. It is black, and this is hematite. Does anybody know what hematite is? It's rust. It's red. So when an iron nail rusts, it forms Fe2O3, and it turns that red color. But if you have a different charge on that oxygen and a different ratio, a different charge on the iron and a different ratio with oxygen, it changes completely the characteristics. So the first one tends to be a black powder, and the second one tends to be a reddish color. So charges on transition metals can change a lot about the compound. Yes? One of them is more stable than the other. Hematite is more stable than wustite. Wustite tends to degrade into actually a different iron compound. Yeah, excellent question. I would like you to give me what do I want you to do? Okay, how about you, I have, for practice, I'm going to have you match Cu plus and Cu2 plus with the common chlorine ion. Write this out for me. Actually, I'm going to make that a little harder. The common sulfur. Yeah, so I want Cu plus with sulfur, and then I want Cu2 plus with sulfur. So with the sulfur ion. just like I did with the two charges of iron with oxygen, I want you to do the 2 charges of copper with the sulfur ion. So it's kind of bluish black. Yes. Have you seen Firefly?
Oh, wait, the show? Yeah.
I love their swearing, like how they make that like
I wish they would have been more quiet. It's like, wasn't there one that they used like loud?
yeah, go around. And then they like, but then alrighty. Cu plus, how does it combine with sulfur? Yeah, so what's the charge on sulfur for when it becomes an ion? 2 minus. So in order to cancel out the 2 minus, you need 2 plus, which means it's going to be Cu2s. And then what about the Cu2 plus? Just Cus. I want you to do one more, and that is Mn4 plus and oxygen ion. So this is yeah, you know what I'm doing this. What? I will show you. Yeah, you're supposed to, I mean, that's the, but I have this specific example for a particular reason. Yeah. What did you all get? MnO2. Now you notice that can everyone listen up, please? So you could have done Mn2O4, but that's not correct because once again, we want the lowest ratio of an ionic compound. And the reason for that is that an ionic compound, it's not just, if it's NaCl, it's not just one Na and one Cl. It's actually a full lattice, but we describe one unit of that. So for example, let's take a look at what NaCl looks like in terms of on the atomic level. You have Cl is larger than Na because of its location on the table. So you have a negative Cl and then you have a small Na+. I don't have room to write the plus, but and then you have a large minus and a small plus, etc. And because opposites attract, it's going to switch off every one. So it's going to form a lattice that kind of stacks really in 3 dimensions, but it stacks every other one. And this is just this is a relatively simple one in that we have one cation and one anion. So if you had, for example, MnO2, you'd have to place the 2 O's in a particular manner so that it would separate the Mn's, right? Because like charges repel and opposite charges attract. So it's going to switch off your negative and your positive. So what we are describing with the NaCl is the smallest, most reduced unit of that ionic lattice. So we are describing just one of those guys. And that is why we have NaCl instead of like Na. So smallest unit, lowest ratio, yeah. A lattice is a repeating, it's a repeating molecules. Thank you. Questions, concerns? Polyatomic ions. Thus far, we have only talked about monatomic ions. What do you think monatomic means? One. What do you think polyatomic means? More than one. So these nice clean Na plus and Cl minus, that's not the hardest it gets. We're going to go to polyatomic ions. Polyatomic ions look something like this. These are all examples of polyatomic ions. They all have more than one. You hate them. Great. They all have more than one atom within the ion. And I'm going to just tell you that anything with with an atom followed by a certain number of oxygens is called an oxyanion. That's going to come in handy next class. So NO3 minus, SO4 2 minus, PO4 3 minus, those are called oxyanions. So when it's another nonmetal atom followed by any number of oxygens, that is an oxyanion. Polyatomic ions do tend to be negative. However, there is one very important exception. There are multiple exceptions, but one that you have to know. And the the positive polyatomic ion or polyatomic cation that you have to know is NH4+. NH4+ could take the place of a metal in an ionic compound. So you know how I said that the cation in an ionic compound is usually metals? This is the one you need to know. So if it starts with a metal or an NH4, it is an ionic compound. these ions are unique in that all of the atoms within the ion share that charge. So it's not like, for example, an NO3 minus, that minus is on any one specific atom. It's not on one of the oxygens. It's shared. I'm just going to draw this out. It is shared by all of those atoms. The interesting thing about polyatomic ions is that they combine covalent and ionic bonds. So within the ion, you have covalent bonds, which means that all of those atoms are sharing electrons between them. And then overall, it has a charge, which means that it's going to form an ionic bond with another, in this case, cation, because this is an anion. Okay. So if you want to show that ion has a charge that is kind of, it's not localized, it's general in that whole ion, you put brackets and you have a negative sign. And we'll use that more next week. And then, for example, we could have N, H, 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 H. And these could very well, these two could form an ionic bond between the positive and the negative. Okay, so that's what's going on in a polyatomic ion. You have atoms that are covalently bonded but share a charge that then will attract the opposite charge. We tend to balance these very much like we balance our monatomic ions. However, the way we write them can be slightly different. Going to start with the simple sodium, and I'm going to add NO3 minus to it. So based on what we learned with the monatomic ion, what are we going to do to combine these? Nothing. We have a positive 1 charge and we have a negative 1 charge. They are just going to combine to be NaNO3. So the 3 is part of the anion, all right? Because those 3 oxygens are in the anion. K plus and SO4 2 minus. What do we have to do here? Multiply potassium times 2. Can everyone please listen up? Thank you. Which means that we have K2SO4. So in this case, we have multiplied the potassium ion times 2, but we still only have 1 SO4 because that 4 is part of that ion, that polyatomic ion. Okay? We have 2 Ks and then an SO4. Think of that SO4 as a unit. Now you might be wondering what happens when we have multiples of a polyatomic ion. How do we distinguish between the subscript that's in the polyatomic ion and the one that multiplies by it? Well, we use parentheses. So you notice that we didn't have to use parentheses in these 2 because it's clear that there's 2 potassium and then you have the SO4, 2 minus. However, if you have Mg 2 plus and NO3 minus, what do you have to do? NO3 multiplies by 2. So you have 2 NO3s. That means you have a magnesium, and then you're sticking on 2 NO3 minuses, which gives you Mg, but then NO3 already has a subscript in it. So to distinguish between that, we have to put parentheses around it and say we have 2 of those. All right? Only use parentheses when you have multiple of the polyatomic ion. It's not necessary in the top two compounds. It is necessary in this bottom compound. And never ever write this as MgN2O6. That is wrong. Can anyone tell me why that is wrong?
Because 1003 is its own unit.
Yes, it's not a unit. It's not 2 nitrogens and 6 oxygens floating around. You have an NO3 and an NO3, and you need to make that clear in your compound. Excellent. Yeah. Yes. Yeah, and we will definitely take that into account when we get there. That's on the next test. So don't worry about it right now. For right now, I want you to be clear on balancing your ionics, because if you don't have a good basis in writing ionic compounds, balancing equations goes all the way out the window. Yes? Because the second one, you have one SO4, so you don't need to multiply it by any subscript. So you don't have to distinguish between the subscript in the compound and the subscript multiplied by it, because you only have one SO4. In the third one, you have 2 NO3s, which means that, so if you wrote like NO3 without parentheses, it would look like NO32 or something like that. So you need those parentheses to distinguish between the subscript in the compound, in the ion, and the subscript that's multiplying that ion. We'll do practice. And then we also have, let's see. Yeah. And oops, I want what color? NH4 plus and O2 minus. What do we have to do here? So this is using our NH4 plus, which is the only non-metal cation you have to know. And what do we have to do here? Yep, times 2. So in this case, do we have to use parentheses? Yes. So it's going to look like NH4 2O. Question? Yes. I do care if it's a bracket instead of parentheses. It should be parentheses. Bracket means something different. Counting atoms in these, you do have to take into account the subscript in when counting these ions. So how many oxygens do we have in that third compound? 6. So because we have 2 NO3s and each NO3 has 6 oxygens, so if you're just talking about like how many oxygens atoms are in this compound, you do have 6. So how many nitrogens are in the fourth compound? 2. And how many hydrogens? 8. Right? Because 2 times 4 is 8. Practice. So write the compounds of, and that's a terrible 4. So for the aluminum and the barium ion, you have to figure out the charge and then balance it. Oh,
Because remember how she said that means you have 6 of them. So I'm going to go ahead. It's all together. Yeah. So you want 2 of those together.
Yes.
Yeah, so you want to carry that 2 over that 206.
Right, so times 3. And then what about for this one? No. So then that's going to change slightly on that. Exactly. So the most you'll get is like 3, like 4 less. Cn minus is a polyatomic ion. Okay, I've seen a lot of people forget that in writing. Yeah. It's actually a cyanide. Yeah, you'll learn that. That's actually the easy. So when you like put someone the cyanide, it's not just cyanide. But it's very so I'm saying that like if you say like yes. So the more you know, like figure it out. You're going to we're gonna start today. I like it.
I just don't like
Yes. I think all of us. No, I love it. Yeah. Well, it wasn't my favorite. It wasn't my favorite. But I did go a little bit like Numero uno. What do we have to do? Nothing. We can just combine them. CuSO4 because we only have one SO4. We don't have to use parentheses. How about what's the charge on the aluminum ion? Al3 plus, which means what do you have to do? Multiply that cyanide ion, Cn minus, by 3. So what do you have to make sure you include there? Parentheses, because you have Al, and that 3 applies to both the carbon and the nitrogen. Yes.
Let's say in the exam, I was number 1 with the parentheses. Would it still wrong?
I might take off half a point out of like 2 or 3 points. Yeah. She just asked if you put the parentheses in when you shouldn't have them, will you get points off? Not a lot, but probably a little. What's the charge on the barium ion? So how do we balance those? Times 3 and times 2, so we definitely need parentheses on that one. Ba3PO4 2. So notice that barium does not need parentheses because it is a monatomic ion, but phosphate, PO4 3- is a polyatomic ion. So when you multiply it, you need to have that subscript. Yes, you do, because that 3 cyanide, Cn minus, is, even though it doesn't have a subscript, that 3 applies to both the carbon and the nitrogen. If I just put AlCN3 with no parentheses, it would just mean 3 nitrogens, not 3 carbons. So whenever you have a polyatomic ion, you need to have that parentheses with the subscript outside. We are going to get a little intro into naming. Naming is all we're going to do next class. So we learned how to write these today. Now, how do we name them? I think I'm just going to talk about the cations. There will be many, many rules that you'll have to remember from next time. This is the first of them. And cations have 2 types. There are cations that only can have one. There are elements that can only have one charge and one positive charge, and then there are elements that can have multiple positive charges, as we saw today. So what's an element that can have only one positive charge? Potassium. Also calcium. Calcium can have 2 plus. So it's not it's not that it's always 1 plus. It's that it can only be 1 plus, or it can only be 2 plus, or it can only be 3 plus. Okay, it has one charge state that it can be. Okay, so potassium, calcium, aluminum, 1 plus, 2 plus, 3 plus. That's the only charge it can have. So that is a type 1 cation. So only 1 charge. So, and these are main group cations. Does everybody remember what the main group is? Yeah, so alkali earth, and then that 3 plus row under boron. So main group is not transition metals. However, there are 2 transition metals that are type 1 cations that can only have 1 charge. And I know this is, and there will always be exceptions. So the 2 exceptions are Ag plus and Zn2 plus. so it's main group elements and main group cations and Ag plus and Zn2 plus. So it's any of those that are in the 1 plus, 2 plus, and 3 plus rows, and then Ag and Zn are also type 1. And there's actually a really helpful little trend here. Okay, so if you look at Al, what's the charge on Al? 3 plus. And then, what did I just tell you the charge on zinc is? 3, 2, 1. Goes in a diagonal. So that's how you remember that it's zinc and silver, and those are the charges. So it goes aluminum 3 plus, zinc 2 plus, silver 1 plus. So those are the two transition metals that are actually, that can only have one charge. These, the naming for this is really easy. So we will combine the cation and the anion naming, but first, so you name it, an ionic compound with, since you have the cation first, you give the cation name first. And the easy thing about type 1 cations is you don't do anything. So if it starts with Na plus, you're just gonna write sodium, and that's the name of your, so for example, let's see if I just had like NaX, okay, so whatever is followed by sodium, it's going to be sodium something, and then you would put your name of your anion. So we will talk about the anions next time, I don't have time, but it's just sodium something, okay, you don't have to change the name at all, which is great. Type 2 cations then are what? They can have multiple charges, and they tend to be transition metals. So the transition metals, except for silver and zinc, and once again, 2 exceptions. What is this? Tin, that's what you have to know, and lead. Tin and lead can have multiple charges. So those are the 2 main group elements that are type 2 cations. And if you look at your periodic table, you'll notice that for tin and lead are in that column that you don't know the charge for. It depends. So basically, a type 2 cation is any cation that if you looked at the periodic table, you'd be like, I don't know what the charge is. Because you don't have those trends. The only exception to that is silver and zinc. Okay, so if you look at lead and tin, you're like, we didn't learn what the charge is for group 4A. And that means that tin and lead, you have to define what the charge is because they're going to be multiple charges. So for these type 2 cations, you have to put the charge in Roman numerals in parentheses. So put charge in Roman numerals. So for example, if you have FeX, followed whatever, it's either going to be iron 2X or iron 3X, depending on the balancing. Okay, so for type 2 cations, you have to define what that charge is because any chemist looking at the periodic table wouldn't be able to tell what that charge was. What? Just any element, like any other anion. It's just a substitution for an anion. Oh yes, and then ammonium, so NH4 plus, we're gonna talk about the naming of the cations. What? Oh yeah, it is type, oh yeah. Ammonium's the other type 1 cation, it can only have 1 plus charge, thank you. And you'll learn the name, you'll have to know ammonium, but we'll talk about that later. Questions? Oh, sorry, that's NH4 plus. Not NH plus. Questions? Let's do a worksheet.